This is Jeremy Manson. Those of you who come every week will know that this is the series of talks on advanced topics in programming languages. Before we start every talk, usually it's a different speaker, but before we start every talk I like to make a plug for other people to come and give talks. So if you are an expert in something, usually programming languages or software engineering related, but doesn't necessarily have to be, then please come up to me so that we can arrange for you to give a talk, because everybody else is in fact interested in hearing what you have to say. All right, so having said that, I am the speaker today, and I will be speaking about the Java memory model. Exciting stuff. By the way, it says Google Confidential in the corner here. That's because the template said Google Confidential. It's not really confidential. I'm not going to talk about any confidential material today. You can feel free to ask me questions, but don't ask me confidential questions because the video is going out live. Right, so the Java memory model, this is really about concurrency in Java. And what I'm going to do today is I'm going to talk about how you can understand the building blocks of concurrency in Java and how you can use them to make effective and efficient code. All right, so this is basically the rundown of where I'm going to go today. I'm going to talk about the scope of the talk a little bit for a few minutes, and then I'm going to talk about the basics, the fundamentals, the underlying principles behind concurrency in Java. And then I'm going to talk about thread-safe lazy initialization, because that's a topic that comes up a heck of a lot, and it's good to have something on the record about that. I'm going to talk about how you can use final fields to have decent design patterns in Java, and I'm going to make some very generic recommendations at the end about how to design concurrent code. It's nothing terribly specific, but hopefully it will be enlightening. All right, so the Java thread specification, it was revised as part of JSR 133. That's a Java specification request, number 133. And it was incorporated into JDK5, so it's in JDK5, JDK6, and all future JDKs. We had a few different goals in revising it. If you actually look back at the original Java thread specification, it was really, really impossible to understand. And even the people who were supposed to understand it, like the VM writers, they couldn't understand it, and they did all sorts of things that violated it, including optimizations in their JVM that actually violated the specification and things like that. So we had a few goals in the revision. One of the goals was you make it clear and easy to understand. Well, if any of you have actually looked at it, you know it's a little tricky to understand, but you make it clear and make it so that every question you ask actually has a clear answer. The goal is then so that programmers can look at it and write reliable multi-threaded code that they know what it's going to do, such that they know what's going to do, and that compiler writers and VM designers could also look at it and say, I'm performing this compiler optimization, I'm performing this transformation, that's a legal transformation. I have to, as a JVM writer, I have to provide this guarantee, I have to provide that guarantee, and really know what they were supposed to be doing. Okay. This isn't always so easy. Most of you have probably programmed multi-threaded systems before, and a lot of what immediately come across as intuitive assumptions don't necessarily hold in multi-threaded systems. There are some very widely used idioms, or some idioms that have been very widely used, some suggested idioms, that we're going to talk about a little bit later, but that aren't safe. So for example, something called double-check locking, which is going to come back to that thread-safe lazy initialization that I mentioned a little bit earlier. Checking non-volatile flag for thread termination, which I'm also going to talk about a little bit later. And unfortunately, as undoubtedly everybody in this audience is aware, you can't actually depend on testing to catch these things. Because, first of all, certain anomalies are only going to happen on certain systems. Depending on your cache behavior, on some multiprocessors, but not on a uniprocessor, or on some multi-core processors, but not on multiprocessors, and so on and so forth. So it's very platform dependent. Some of these behaviors are very platform dependent. And furthermore, you can run a test, and then repeat the test, and get a completely different behavior. You can run a test once, repeat it, and then, because thread interleaving is non-deterministic, it's hard to recapture what you've done. So, let's see. In this talk, like I said, I'm going to talk about the basics, the building blocks of synchronization, what it means to synchronize in Java. I'm going to talk about both language primitives that synchronize blocks, volatile fields, final fields, and util.java.util. When I say util.concurrent, it means java.util.concurrent. I just didn't want to do all that java dot typing. and java.util.concurrent abstractions. I'm going to explain what it means for code to be correctly synchronized, what it is that you have to do to write correctly synchronized code in Java. And I'm going to try to convince you that if you're not using synchronization, you're doing something wrong. And not only that, but if you don't need not to be using synchronization. Most of the time, what you're doing in the synchronization doesn't really cost very much. Okay. All right. So again, we're going to be talking mostly about synchronized methods and blocks and volatile fields, and we're going to talk about final fields also. A lot of the same principles, and I'll come back to it, apply to the JSR 166 classes. JSR 166 means java.util.concurrent. That was the number of the specification revision that got us java.util.concurrent. And we'll talk about final fields and immutability too. So, all right. So this is a slide I like because it's my taxonomy slide. At the top is what you really should start out trying to do, and at the bottom is what you should never ever ever do. And in between there's sort of gradations of this is more permissible. So at the top is high-level concurrency abstractions. If something exists in java.util.concurrent, use it, because java.util.concurrent is a very, very nice library that includes a lot of things that you definitely want to be able to do. If that fails you, if you can't find what you want to do, you'll have to program it yourself, sadly. And so you're going to sort of fail over to low-level locking. And you'll use synchronized blocks, or you'll use java.util.concurrent.locks. There are different locks in java.util.concurrent that don't quite mirror the behavior of the locks that are built into Java, the synchronized locks. For example, there's a reader-writer lock. There are fair locks, whereas regular Java locks are not fair, and so on. If those fail you, if you can't stand having blocking in your code, and you really need the efficiency, then you can fail over to low-level synchronization primitives, like volatile variables and the atomic classes. This is already treading into the zone where experts kind of feel like they don't want to do it, but they will do it, and try very, very hard to get it right, and it takes a long time and a lot of thought. But this does allow for non-blocking synchronization. So if you want non-blocking synchronization in your code, you're going to have to use one of these mechanisms. And then deliberate under-synchronization. Doug Lee is actually a really, really smart guy and wrote the java.util.concurrent classes. And he has tried to reason about what happens. He's tried to write classes and reason about what happens when you don't synchronize your code correctly. And he gets it wrong. It's a really, really hard thing to get right. So if this is proof by intimidation. If he can't get it right, then you can't get it right, and I can't get it right. So just avoid it and don't do it. Yeah. All right. So that was the that was the scope. That's where we're going to go in this talk. And let's talk a little bit about the fundamentals. So what do we think of when we think of synchronization? Well, usually when somebody thinks of a mutual exclusion lock, like we have in Java, you think of, well, I try to enter the mutual exclusion lock, and anybody who tries to acquire the same lock is going to block until I release that lock. And that's very important. That's a very important property of a mutual exclusion lock in Java or in C++ or in any other language. But it turns out that's not the only property of a mutual exclusion lock. There's also this property called visibility, which ties into a property called ordering. We'll talk about it. So it turns out that when I use a lock, it determines when another thread sees the updates that I've performed in my thread. So if I write to a variable in one thread, whether or not that write gets seen by any other thread is very heavily dependent on the kind of locking I used. And if you don't use the right kind of synchronization, the right kind of locking, then your compiler and your processor and the whole underlying system are allowed to conspire to destroy this. And break your code if you wrote it in such a way that expects this these sort of strong visibility properties. So it's something that I'm going to come back to again and again. I've already come back to it twice, I think. Here's a third time. People worry a lot about the cost of synchronization, but the cost of getting something wrong and having it be in production is a pretty high one also. And so a lot of people will try to devise some sort of weird scheme to communicate between threads without using explicit synchronization. This doesn't work. You can't get away with not using a lock or a volatile or another concurrency abstraction. I know I'm beating on this kind of hard. I already said that Doug can't do it. All right, so let's see. All right, so here's my basic example of why this is a hard thing to do. Here's an example. It's got two threads, thread 1 and thread 2, and it's got two variables, x and y. And x and y are both initialized to be 0 at the beginning of the program at some time. And then thread 1 writes to the variable x and then reads the variable y. And then thread 2 writes to the variable y and reads the variable x. And the question is, can this program result in I being assigned the value 0 and j being assigned the value 0? And well, you think about it for a little while, and you think, well, let's see, if I is assigned the value 0, that means that that read of x somehow came before the write to x. So there is, some sort of thing that orders the read of x before the write to x. Okay. And if j is assigned the value 0, well, that means that there's some sort of ordering in the program that means that this was assigned the value 0 before y was assigned the value 1. So there's some sort of ordering that reflects that. And so now we have a situation where the write to y occurs before the read of x, occurs before the write to x, occurs before the read of y, occurs before the write to y, occurs before the read of x, occurs before the... I could go around like this for a while, but I think I don't have that much time. So it sounds like this should be something impossible. Now, I was thinking about, at this point, asking people if this were possible. I'm sure there's a large segment of this audience that knows that this is possible. But the fact is, it's a little disingenuous, because I wouldn't have put it up on a slide if it weren't possible. I wouldn't have bothered to put it up there. So, of course, yes, this is totally possible. The fact of the matter is that compilers and processors and VMs and all sorts of things can actually change the order of independent accesses in your program. A compiler can look at thread 2 and decide, or a processor can look at thread 2 and decide that those two actions would be more efficient if they were performed in the opposite order. So it can just switch the order around. And what happens in that case? Well, maybe the read of x will occur before the write to x, and then the write to x will occur before the read of y, and then the read of y will occur before the write to y. And you get that kind of loopy, queer result. Okay, so again, how can this happen? Well, there's a whole bunch of ways in which this can happen. The compiler can just decide to do it. It can decide, well, on my processor that I'm compiling code for, it's just more efficient to switch them around. The processor itself can reorder them. Processors do out-of-order execution. On a multiprocessor, you might have the values not be synchronized to global memory. So imagine if, for example, x and y were both stored, those two threads were executing on separate processors. And on one processor, x read a stale value, the processor read a stale value for x, which was 0, and another processor had a stale value for y, which was also 0. So on a multiprocessor, these values might not have been pushed out to main memory yet. The memory model, the Java memory model, is designed to allow you to do all of these things, allow the processor and the compiler and so on to do all of these things. And we tried to give it wiggle room so that there are even optimizations that nobody's actually performing that we said, oh no, we have to allow this. It's great for your performance. This sort of stuff gives you this, these first few bullet points, they give you, orders of magnitude speed up in your code. So they're absolutely necessary. But unfortunately, for a lot of people, it's bad for their intuition about what's actually going on in their code. Let's see. Did I put in a slide? Okay, so I should point out that this is obviously incorrectly synchronized code because you're not actually locking. But I think probably most of the people in this audience are familiar with threads and locks on some level and know that if you're actually accessing the same data, you need to use a lock. All right, so this is the slide in my talk where when I give this talk, I always say it's the most important slide. One time to really underscore that, I took the microphone, put it right up to my mouth and said, "This is the most important slide in the talk." Unfortunately, the videographer yelled at me, so I'm not going to do that today. But this is, in fact, the most important slide in the talk. This is the takeaway slide, if you like. And don't worry, everything isn't up on it yet. There are two threads in this example. One thread is doing a bunch of writes, and another thread is trying to read the writes that the first thread performed. The first thread is writing to a field called X, writing the value 1 to a field called X, then acquiring a lock called M, and then writing a reference to that object that contains the field X out to somewhere in global memory, and then unlocking M. At some time later, for some definition of at some time later, along comes thread 2. Thread 2 acquires the lock on M, tries to read the reference to the global variable, and then tries to read the field of the global variable that thread 1 earlier wrote. The takeaway message is that everything that occurs before an unlock, all of the writes that are going to occur here, are going to be ordered before and visible to everything that happens after, excuse me, that happens after a subsequent lock on the same object. So what does that mean? That means in the second thread, all of the reads that this second thread performs, this read of glow and this read of X, are going to be ordered after all of the writes that this first thread performs, so that all of the updates performed by this first thread are going to be seen by this second thread. And that's because this unlock and this subsequent lock on the same object create a sort of pair of something that we call a release and a subsequent acquire. And you can sort of think of this as being the release pushes out the updates that this thread made along this edge, and the subsequent acquire sort of looks at this edge and grabs the updates that were performed by thread 1. And so it will know that the values that were written in thread 1 can now be seen. So is it still off? Oh no, it's on now. Okay. All right. So yes.
Basically only fulfills the basic contract that's required, so that you can run code and make sure that it satisfies the properties. So the question is, has anybody?
Is this actually on? Am I?
So the question is tell me on when you ask.
Something going on?
Battery.
Oh, okay. Well, here, let me swap out battery. This thing on? Yes, this works. Okay, so the question was, sorry? No, the videographer still has his earphones on, and that's why it's really a bad thing, because they all of a sudden get this really loud noise in their ear. All right, so the question was, has anybody implemented a VM that sort of fulfills the minimum properties such that, so that you can really guarantee that your code is doing the right thing? There are other factors at work here. One of the factors is that you have to sort of say that this thread 2 is going to come along at some time later, right? And so you do end up with this sort of notion of you can have different interleavings among the actions in your program, and that can be a real problem when trying to implement a JVM that does the minimum, because you're not going to capture all of the behaviors of your program because of the different kinds of interleavings you can have. Basically, multi-threaded programs are non-deterministic. You can have non-data related race conditions, and so there isn't a VM that will execute, that will give you all of the possible executions of your program so that you can ensure that it's correct. There are simulators available that will sort of take small snippets of your program, try out every single permutation, and come back with a set of available results. But for a whole program, it's not something that's been implemented. Let's see. All right, moving on. Yes? Okay, moving on. All right, so I mentioned the notion of release and acquire, and got a smart audience, which is nice. All memory accesses before a release are ordered before and visible to any memory accesses after a matching acquire. So this is going back. I mentioned this terminology before, and I'm going to be coming back to it again and again. There's a release when you perform this unlock, and there's a subsequent acquire when you perform a later lock on the same object. Okay. Right, and I'm going to be coming back to release and acquire as terminology again and again. So it's a good thing to keep in your mind. This establishes a release and a subsequent acquire establishes something called a happens before relationship. And in addition, execution order within a thread also establishes a happens before relationship. So I'm going to use the words happens before again and again. And actually, it's something for you to get used to, even if you're not a Java programmer, because C++ is also adopting this terminology for their threading model. What it basically means is that, that instruction happens before the first instruction in thread 1 happens before the second instruction in thread 1, happens before the third instruction in thread 1, happens before the fourth instruction in thread 1, which happens before this subsequent lock on the same monitor, which happens before all these instructions. And happens before is transitive, so you can talk about, say, the first instruction, the first action by thread 1 happening before the last instruction in thread 2. The opposite of happens before is happens after, right? Sometimes I say happens after and assume that people know what I mean, but they don't always. Yes?
That's referring to just instructions and not lines of code, right?
Yeah, it's actually, yeah. It's referring to not lines of code. It's referring to actions in flight, if you will. So what the VM is actually doing. And sometimes I'll say statement instead of action, which is really a bad thing to do. It's not the static program statement that has the happens before. It is the dynamic, I just executed an instruction in the VM, and that's what has the happens before order.
Someone was waiting because it has lines of code up there.
Yeah, I mean, you could also imagine this as what is being executed by a VM. Yes, Dan.
So just a clarification.
Oh, I didn't repeat the question. Okay, I'll keep it in mind for later. Sorry. Yeah.
Just a clarification on the slide. You assume that thread 2 is starting later than thread 1 because you could have the...
Right. So the question was, do I assume that thread 2 is starting later than thread 1? Yes, I sort of referred to that. I alluded to that when I talked about this earlier. I said that at some point later, for some ill-defined notion of at some point later, which I don't want to get into, thread 2 comes along and performs a lock. Yes, at some point, thread 2 is going to start, and it is, in some sense, happening later than thread 1 ends. So yeah, that assumption is built into this slide. All right, and I'll try to repeat the questions from now on. I apologize for that one I missed. Okay, so a data race. So if there are 2 accesses to a memory location, and at least one of them is a write, and I meant to take out that thing about volatile, so don't pay attention to that thing about volatile. Then the accesses must be ordered by happens before. Otherwise, you're in something called a data race. And if you recall the first example I showed you with X and Y being read and written in the opposite threads, that was a data race because there was no synchronization between the 2 threads. There was no ordering between the 2 threads establishing a happens before order among X or among Y. If you violate this property, if you have data races in your program, it's really, really hard to figure out what your program is going to do because the compiler and the processor and all of these things, in addition to not having locking and all of those good things, the compiler and the processor are going to conspire to violate what you think it might happen. It's not as unspecified as a buffer overflow in C. We were very careful about that when designing the memory model, but it's still kind of hard to figure out what's going on. Yes, Alex?
Is there any chance to check, not guarantee that you're not violating the property, but at least planning for a compiler to catch some violations?
Okay, so the question was, can compilers catch violations of this? Yes, there are various tools. There are various tools that will allow you to check for data races in your program. I don't know which ones are in wide use here, but I know there's definitely a program called JProbe which will do it for Java programs. And it's definitely an area of ongoing research, and I think that we're going to see more of it as these issues become more and more important. But it's definitely something that people try to do. There are various different kinds of methodologies for doing it, and we can talk about some of those methodologies later, but we're not going to have time in the talk. So a lot of people will think about these things not in terms of happens before, but in terms of memory consistency operations. So I decided to put together a slide that talks about them in terms of memory consistency operations. It talks about what actually happens when you go onto a machine. So you have these. This program, and you encountered the synchronized block, and it will block until you obtain a lock, and then it will reconcile what's going on in memory with what's going on in your cache, and then it will, at the end of the synchronized block, it will push the values you have in your cache out to memory, and then it will release the lock. And that's actually what happens. Maybe that's not actually what happens. Maybe I was just a little bit disingenuous there. It turns out that this is not what happens, especially in Java. A lot of people going into C++, coming from C++, are going to expect those sorts of coherency behaviors, those sorts of memory actions when they use Java locks, and you're not guaranteed to get them. So for example, in Java locks, you are allowed to take accesses that are outside your lock region and move them inside your lock region. So you can take this you can take that first line, that read of O.field, and you can push it down inside the synchronized block. That's called lock coarsening. Now you can move, obviously you can move accesses in, but you can't move them out. So we actually call that Roach Motel ordering, because accesses come in, but they don't go out. That's a television commercial from the 80s, which probably almost nobody in this audience remembers. The other thing to remember is that a release only matters to a matching acquire. I mentioned before an unlock followed by a subsequent lock on the same variable. But the fact is, in some cases, there may not be subsequent locks on the same variable, and your compiler might be able to detect that. So for example, in Java, a lot of times what will happen is that you have a lock on a thread local object. And a lock on a thread local object doesn't do anything because there's no matching acquire in a separate thread, because you're only locking it or unlocking it in one thread. So there are compiler optimizations built into this in Java SDK 6. Also, reentrant locks don't have any defined semantics. So if you acquire a lock and then acquire the same lock, that second acquire doesn't do anything, isn't guaranteed to do anything. So you can see a lot of cases where you can put these lock and unlock operations in, and the compiler isn't actually required to do those sort of reconciling out to main memory, bringing stuff back in from cache type behaviors. All right, so don't rely on locks flushing stuff, basically, is the moral of those two slides. All right, so those were the fundamentals. I've talked about the happens before ordering and why it's really important that you use that as your mental model. Somebody, by the way, is going to come in and talk about next week why he doesn't want you to use that as your model, but I disagree with him. Needless to say. I'm going to talk a little bit more about some of the finer details in the memory model now, including the volatile variable. So, okay, so I mentioned before this concept of data races. If a field can be accessed by multiple threads at the same time, and at least one of those accesses is right, you should really access it within lock regions. You should really make sure that locks protect those accesses to those fields. Another alternative is, if you don't want to use blocking synchronization, if you want to do something that's non-blocking, you can mark the field volatile, and that will give you some essential virtual machine guarantee. It will say to the VM, I want certain special guarantees here. And also, it's very nice to do that in general because it serves as documentation. It means this flag is meant to be shared among multiple threads. It can be tricky to get volatile right, but again, I'm going to go back to what I said at the beginning. If you don't use any synchronization, then your program just isn't going to work. So volatile ends up being an important component of doing non-blocking synchronization in Java. What does volatile do? Well, I'm going to go back to that sort of general vague notion of at the machine level, what does it do? Well, reads and writes, you can think of the reads and writes as going directly to memory if that's the mental model that you prefer. Again, there are caveats for things like thread local volatiles, but if you prefer that sort of mental image, that's what it does. Volatile longs and doubles are atomic. One of the properties of regular 64-bit integers and doubles in Java is that they actually are allowed, Java virtual machines are allowed to write 32 bits at a time. So you can write the first 32 bits out, and then another thread can come along and see the new first 32 bits, but the old second 32 bits. So it can look like some garbage value came in there. I think that was done, I'm not sure how many modern JVMs still do that. I think that was actually done for the Alpha processor way back in the day. But the guarantee is made for volatile longs and doubles that all 64 bits will be written. You're never going to see the first 32 bits from one and the second 32 bits from another. That's one of those anecdotes that I like. It's not it's not necessarily integral to what we're talking about here. But going back to the notion of what's going on at the compiler and VM level, volatile reads writes are not generally going to be reordered, and reads writes acquire release pairs. That's the most important notion to remember here. That what you end up having is that volatile writes followed by volatile reads are going to be a release and a matching later acquire. So a volatile write happens before all following volatile reads of the same variable. And in this way, you can think of a volatile write as sort of being akin to a monitor exit, which is just what we call an unlock in Java. And a volatile read is going to be similar to that following later lock on the same variable. So how does this come into action? Well, hold on a second. I'm going to grab another drink of water here. Thanks. All right, so I talked a little bit before about a situation where you can use volatile flags, or you can use volatile flags to as a flag for termination of a thread. So let's look at this example. We've got we assume that there are two threads. One runs the run method here, and the other eventually calls stop. And what happens in the run method is it continually iterates until the stop flag is set. And what happens in the other thread is that eventually it will call stop, and stop will be set by that method. And in theory, the theory is that the first thread will come along, do the next iteration, see that the second thread has set stop, and then say, oh, well, while not stop, it's stopped now, and exit. It turns out that if you don't use volatile here, a compiler can look at this first thread, at this run thread. It can say, what's going on here? Well, I'm reading stop on every iteration through that loop, but I'm not updating stop on any iteration through that loop, so the value of stop is never going to change. Well, if the value of stop is never going to change, I can test stop once at the beginning, and then otherwise just have an infinite loop here. Why bother to keep going out and reading stop? So a compiler can actually transform this run method without volatile. A compiler can actually transform this run method into an infinite loop, which is a really nasty thing to have happen to you. So it's very important in cases like this to declare your variable volatile. And your compiler will look at that annotation and say, oh, that's a volatile variable. I'm not allowed to perform that kind of transformation. And it will leave this alone. It will actually go out and read the value stop on every iteration through this loop. Yes, Alex.
That extra close phrase just to try for?
This one matches that one. And this one matches that one, right? Okay. Yeah, no, it's just because, at some point you run off the end of the slide. Yeah, sorry about that. Yeah, I'm sorry. This is not conformed to the style guide. Yes.
If it wasn't volatile, wouldn't the compiler still know that because stop could be called that it should be updated? So would it make an optimization?
So the question was, if this was not volatile, wouldn't the compiler still know that stop could be called? Compilers perform the typical compiler transformations are performed on single-threaded code. And you look at what can happen until the next iteration of this loop in a single-threaded context. So it only looks at what goes on here, and assuming one step doesn't invoke stop, and it looks at what goes on here. It sees that stop is not set anywhere in the loop, and it can then perform that transformation based on the fact that it's looked at just at what can happen in this thread. And this is actually a fairly important thing to do, because if you have to do compiler optimizations based on the notion that other threads are going to be going in and changing your data all the time, you're not going to be able to perform any compiler optimizations, because a lot of them have to do with assuming that the same value is used for a variable over and over and over again, or that a variable's value doesn't change. So use volatile here. It's an important thing to do if something can come in and update and be updated via multiple threads. Yes.
Do you know of a compiler that
Off the top of my head, I don't know if any of them do, but it's not an unreasonable thing to expect. I mean, it's one of those things that some compilers have said don't do this explicitly, but it would be very easy to take out the block that says don't do this explicitly. So it's it's something that I could very easily see it doing, basically.
I'm pretty sure I've seen that actually happen in my own code.
Matt Frantz says it's happened to his own code. So yes is the answer. But it was a long time ago, and undoubtedly compilers don't do anything like that now. Yes?
This code is kind of hard to structure it like this, but it could be in a way that, it would be, the question is it equivalent to having the reading of the stop and sign of a try catch block in terms of how much penalty it is to use the volatile?
No, I'm going to get to that. It's not, there's no penalty to using the volatile in this case. Well, there's very little. I'll get to that. That's one of these misconceptions. The other part of volatile, in addition to that sort of ordering thing, as I mentioned, it has a happens before relationship. So the question was about the performance impact of volatile. Sorry about that, VC guys. The question was about the performance impact of volatile, and I'll get to that later. So here's a very similar situation. And the reason I sort of sped along is because we've only got 20 minutes left. I want to get it all in. So we've got two threads again. One of them is going to set the value of data, and then when data has been set, it's going to set a Boolean flag saying we've set data. And another thread is going to check that Boolean flag, and if that Boolean flag has been set, it's going to say, oh well, we've constructed data, so return it. And if we haven't constructed data, then it's going to return null. So if we don't use volatile here, what can happen is in the second thread, the compiler or the processor or the VM could just reorder the data equals O with the ready equals true. So what would happen was it would set ready to true, and then maybe the other thread could come along, it would set ready to true first, then another thread would come along, perform get, check ready, it would be true, but we haven't, in this first thread, we haven't set data yet, and it would return data, which is some garbage value, some old value, maybe null.
Why can't it reorder ready to getting, so your only promise was about volatile read writes, not about...
Well, so it can't do it because this is a volatile variable.
Yeah, but you said about volatile.
No. So volatile also, I don't know if I mentioned this clearly. Volatile also implies a happens before relationship. See, there's a little arrow there now. So all of the accesses that happen before, you can imagine that slide I had with the cones before, which is why that was such an important slide. All of the writes that happen before this write to ready are going to be ordered before and visible to all of the reads that happen after this read of ready in the second thread. Does that answer your question? So Frank's question was basically, why does that work? Well, you can look at the actual memory model and we can...
I see why the data equals 0 is ready could be ordered, at least according to your previous definition.
Well, there's a happens before relationship. Well, okay, so we can talk about it later. We can talk about it later. There are more questions about why this works, and obviously this is something that a lot of people have a lot of questions about. Here's some more simple notes on volatile. Incrementing a volatile is not atomic. If you have a volatile int v, v++ means v equals v plus 1, which means that you read v first, and then you increment the value you read, and then you write it. And if between that read and the write, somebody else wrote to that volatile variable, you're not going to get an atomic increment. So that's something that a lot of people sort of have to think twice about. Volatile reads are very cheap. This is a question that we just had about the performance of volatile. Sometimes it's only the compiler optimization cost. Specifically, on an x86, there is no cost to reading a volatile variable. There's a cost to writing to a volatile variable, but there's no cost to reading it. You don't have to perform any additional memory barriers because the coherence guarantees of the x86 provide this for you. And so you do have to sort of prevent yourself from doing compiler optimizations around volatile variables, but you don't actually have to do anything additional in terms of coherence operations as of 2007. There's no way to make the elements of an array individually be volatile. If you say volatile int array, that means that the reference to the array is volatile, not the elements of the array itself. So if you say array sub 1, that's not going to be a volatile. If you write to array sub 1, that's not going to be a volatile write. If you want any of these properties, consider using the java.util.concurrent.atomic package, which has things like atomic increment and compare and set and atomic integer array, atomic byte array, blah, 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 so that you can actually get those sorts of semantics. And they have otherwise they have very similar semantics to, atomics have very similar semantics to volatiles in terms of happens before relationships. So there's some other happens before orderings, like if you start a thread, everything that happened before you started that thread is going to happen before the actual start of that thread. And the same thing is true of joins, but only in the opposite direction. And there are lots of things in java.util.concurrent that set up happens before orderings. Like if you put something into a queue and then later take it out of the head, then that sets up happens before ordering, and so on and so forth. It's pretty well documented, so if you have more questions, you can ask me later. All right, so I want to get on to thread-safe lazy initialization, and we have 15 minutes, and we're not going to have time for any questions, but don't worry, there'll be plenty of time to ask questions. Plenty of opportunity, excuse me. So the principle behind thread-safe lazy initialization is that you want to perform lazy initialization, you want to perform initialization of something, but you don't want to perform it right when, of a singleton, of something that you only want one copy of. You don't want to perform it right when the JVM starts. And you don't want to incur the synchronization penalty of locking every time that you want to access that data. So a very common way to do it until recently has been this, which is called the double-checked idiom, or the multi-threaded singleton idiom, some people call it. And what that does is you invoke a method called getHelper. It checks to see if helper is the pointer to this object that you want to initialize. It checks to see if helper has been initialized. If it can't see that helper has been initialized, it acquires a lock, checks to make sure that you haven't initialized it between when you last checked if helper was initialized and now. And then if that is, if you haven't initialized it, then you initialize it and you finally return it. Now the problem with this code is that there are that you have the locking on the writer side. You have the locking on the side that does the construction of helper, but you have no matching acquire on the side that's going to be reading helper. You don't set up a happens before relationship. You do this synchronized block only when you read helper is equal to null. Well, another thread might come along, accidentally read helper is equal to null, but not see all of the other updates performed by this thread. And then it will see helper is not equal to null, and it will return a junk value for helper. So it's actually really important to get the happens before relationship working here. And the way to get the happens before relationship working here is really, really simple. You can just add the volatile modifier here. And I don't think I have time to go into this in that much detail, but that's the basic principle behind that. For an even better solution, I hope I have an even better solution here. Yes, so lots of people have tried to tell me that this works without synchronization. It doesn't work without synchronization. Don't tell me it doesn't work without synchronization. I don't want to hear it. A much better solution is actually to use lazy static initialization, lazy class loading to initialize your singleton value. So there's something in the book called Effective Java. It's a very, very effective book. It's an excellent book. It's by Josh Block, who works here at Google. And it's called the Initialization on Demand Holder Idiom. And how much time do I have? So I probably have enough time just to give you a quick overview. It basically relies on the fact that that static initialization is not performed until the first time you access the class to initialize your data lazily. And it relies on the guarantees that are made about static initialization and synchronization to ensure that all of the synchronization that you perform is correctly in place. And I had a much longer spiel about that, but I don't have time for it. All right, so I do want to go over final fields. Final fields are a really wonderful thing. Use immutable objects whenever you can in Java. I'm not going to make claims about any other programming language. There's actually, I think there's a whole chapter on this in the Effective Java book I just mentioned. There's a lot on why you should use final fields. I'm going to restrict myself to, you can maintain invariants without having to worry about the fact they might change, but I'm going to try to restrict myself to the synchronization benefits. If you make all of your fields final, and you don't allow other threads to see the object that you're constructing until the construction is complete. So for example, you don't have a line in the constructor that says some global reference equals this. Then the spec, the Java memory model actually promises that that object is going to appear to be correctly constructed and immutable to all of the other threads in your program, even if some malicious code tries to attack you with a data race. Well, what do I mean by some malicious code tries to attack you with a data race? Well, it means that some piece of malicious code is going to try to leverage the fact that there's no visibility to see an out-of-date value for one of the fields. And this doesn't happen a lot, but it only needs to happen 1 in a million times. It's easy to try to do this 1 million times and have the visibility kick you in the rear. There's an example of this that was actually found in a real, honest-to-goodness live JVM that nobody here is using, don't worry. And the way it worked is basically a string constructor that created a substring of /temp/user. And the substring of 4, 8 basically means you take the offset of 4 until 8. So it's supposed to be that first thing, /temp/user is supposed to be /user. That's what the string is supposed to be. It's from indices 4 to 8. And the way it did this was by saying you have a string, you have an offset into that string, which would have been 4 in this case, and you have a length, which is also 4. And the attack here was a visibility thing where it created this string a bunch of times and passed it to another thread until the other thread saw an offset of 0 instead of seeing an offset of 4. And so what is this thread /temp/user with an offset of 0 instead of an offset of 4 and a length of 4? Well, instead of being /user, the last 4, it's /temp, the first 4. So you were able to see a directory actually change. And if you're dealing with security permissions on a directory and you've got these sort of data race problems, then that's a really ugly thing to see. Nowadays you don't have to do that anymore. This was in a pre-Java 1.5 VM. Nowadays all the strings, all of the fields of string are final, and you're guaranteed for this not to happen, which is a nice thing. There are ways to change final fields. I don't have time to go into them. Try not to change final fields if you can manage it, because it turns out that modern VMs are allowed to do even more aggressive transformations based on final fields. Try to restrict it to just when you're doing deserialization or clone or something like that, and just with blank objects. And I can talk more about that offline. Yeah. All right. So some basic recommendations, and then I'll get into questions. I don't think that any of these recommendations is too confusing. If you can solve your problems using the java.util.concurrent classes, please do so. Not only are they really well written and safe, they're also really fast, because there's a lot of stuff like non-blocking algorithms in there that are really tricky to get right when you try them yourself, and really it's a very nice package, and if you can manage it, you should. If you have to go beyond that, and even if you don't have to go beyond that, understanding the memory model can really give you a sense of how you can go about devising your own concurrency abstractions. Sometimes you're just going to have something that doesn't fit into java.util.concurrent, and you're not going to want to shoehorn it into java.util.concurrent. You're going to want to create your own concurrency abstraction. So you should really take advantage of that. Mostly the memory model just works if you lock correctly, if you don't share variables between threads without synchronization, which all of you should be doing, then really nothing has changed here. You don't even basically have to think about happens before, because you just get the right properties with locking. Knowing the details, though, can also reassure those who obsess over details, like myself, and clarify the fine line between clever and stupid, which basically means that that double-check blocking algorithm, well, somebody thought that was really clever. But it wasn't really clever. It was actually a little bit stupid, because they were being clever but not clever enough. Watch out for useless synchronization. This is one of those little performance tips. If you use a class that was designed for concurrent use in a single-threaded context, you can generate measurable overhead. I said that Java tries to remove unnecessary locking, but doesn't always succeed. So you can, in fact, generate measurable overhead if you use things like vector or hash table or synchronized map when you're not supposed to be using a synchronized map. Substitute unsynchronized classes when you're only using them in a single-threaded class concept. I don't think anybody actually still uses the vector class anymore, but if you do, and you're only using it in one thread, use an array list. Another thing is, in java.io, there are some methods which every time you write a byte, they acquire and release a lock. So if you want to reduce synchronization overhead, you can often have to use bulk IO or to use the java.nio classes, which are much more efficient to doing a lot of things. You should all learn them so that you can use them anyway. Sometimes synchronization alone isn't enough in a class. I can't tell you how many times I've seen this. Somebody found this in the actual JDK in the APIs a couple of years ago. There is a concurrent hash map class in java.util.concurrent, and when you call get, that is thread safe, and when you call put, that is thread safe. But if you call get and then call put, and in the meantime you make the assumption that nobody else has put that value into that thread, so then something terrible is going to happen. So in this case, you could call h.get, some other not find the name you're looking for. Some other thread could then put that name you're looking for into the hash map, and then you could call h.put, and you're now replacing something, which is not a good thing to be doing. So this is what's called an atomicity violation, and it's important to keep an eye out in your code. Concurrent hash map specifically has something called put if absent, but I can't tell you how many times people have said, oh, well, don't worry, concurrent hash map is thread safe. I don't have to think about these issues. Again, concurrent hash map has okay, so I said these things because I'm running out of time here. Documenting concurrency, right. So it's important to write good comments. There are a lot of times that comments are not really particularly well written. Again, like, is an IO stream thread safe? Well, what does it mean for an IO stream to be thread safe? Does it mean that two different threads can both write to the IO stream and it's somehow safe for them to do so? Well, one thread writes one byte and then another thread writes the next byte and then the first thread writes. So you get this sort of garbage list of randomly associated bytes. Well, is that thread safe? What does that mean to be thread safe? So again, it's not as simple as this class is thread safe, as I said in the previous example, where you had this concurrent hash map. I'm sorry to be rushing through all this. I know I've kind of upped the velocity a lot. Look at the util.concurrent documentation. The util.concurrent documentation is actually really nice. There are annotations described in a book called Java Concurrency in Practice. I recommend this book. I'm going to give you in a slide or two information on how to get it. These are neat little annotations, like thread safe means this is thread safe for your definition of thread safe. This means, it's not thread safe. This means guarded by. It means, I'm saying that this field is supposed to be guarded by a specific lock. This means immutable. This class is supposed to be immutable. Some of which are checked by the find bugs utility that's available from Bill Pugh at the University of Maryland, who is actually also my advisor. So my graduate advisor, pardon me. Okay, so yes, use the right tool chain. This is also important. JDK6 includes a lot of performance improvements over JDK5. Linux 2.6, I think everybody in this audience live has probably heard me say that Linux 2.6 is a significant step above Linux 2.4 in terms of threading performance. You can get, depending on what your code does, you can get whole numbers, multiples of speed up by using the right tools. Let's see. Just some general things that I think I've already said in terms of designing fast concurrent code. Make it right make sure it's right first. The way to do it is to reduce your reliance on synchronization without actually getting the code wrong, which is a tricky balance to do, and I think everybody will agree that that's a tricky balance. Anybody who's tried it will agree that that's a tricky balance. Avoid sharing mutable objects if you can. Again, that's the immutability thing. Use the java.util.concurrent classes. Avoid lock contention if you can. If your lock is going to be held for a really long time, try to shorten the length that your lock is going to be held, and so on. And just a couple of slides have wrapped up. Cost of synchronization operations can be significant, but usually just what you need to get it right is not really all that significant. Again, something like the volatile field where the reading is free. Thread interaction needs, so this is the tricky balance. Thread interaction needs careful thought. You need to make sure that your threads are interacting correctly, but you don't want to be too clever about it because then you're going to kick yourself in the rear. And you definitely don't want to have to think about these sort of reordering guarantees that I've been talking about, these reordering problems, that I've been talking about the whole time. So try to avoid data races, because if you don't have data races, you don't have to think too hard about it. Yes, you need a happens before edge to communicate between threads. I've said that 30 times, so that's what this slide says. That's part of the wrap-up. And here are some places to go for more information. This is a really good book on the subject by Brian Getz and et al. And some of the members of AL work at Google, so I shouldn't be too denigrative for AL. But the first place is a page which gives a lot of pointers to memory model information for those of you who want to get really into the details. There's the concurrency interest mailing list, which Doug Lee runs out of Oswego, and it's for not only for questions about the memory model, but it's also for questions about java.util.concurrent. It's a really useful mailing list. And because I knew I would be running out of time now, I'm going to actually try to answer questions about this. I started a blog just for the purposes of answering questions about this talk, more or less. So if you have questions, post them as a follow-up to this blog posting, and I will answer them offline. And now I think we are out of time, but I'm not sure. I'll hang around for a while and try to answer questions. I want to see if I can hang around and answer questions live. Can I hang around and answer questions live? Thank you.